expert for this session has arrived. I welcome you, sir. He is
Thank you.
Dr. Krishna Gopal Sharma. Let me introduce him. He received his BE degree in Electronics and Communication from Madan Mohan Malviya Engineering College, Gorakhpur in the year of 2001. He completed his MTech and PhD in low power VLSI design in the year of 2009 and 13 respectively. After graduation, he started working in R&D department of LML. He served various institutions, namely Modi University, Lakshmangarh and Manipal University, Jaipur. Presently, he is working in Chandigarh College of Engineering and Technology in Sector 26 itself. He has published more than 50 research papers in reputed journals and conferences. He has Google citation index of 185 with H index of 8 and I10 index of 5. He is a life member of ISTE and member of IEEE. His research areas include low power VLSI design and embedded systems. So I welcome you, sir, in this session. So over to you, sir. Let's start this session.
Good afternoon, everybody. So my topic today is ASIC, Application Specific Integrated Circuit. So already you are aware of the microprocessors, microcontrollers, and so many devices are there, which are there in the market. Along with that, there are ASICs, FPGA too. So first of all, the thing is that we have to know why we require ASIC. Already we have the microprocessor, we have the microcontrollers. It means if you want to do any kind of task to be completed, any kind of job to be incorporated, we may require some of the controlling devices. And we already have the microprocessor. So if I talk about the ASIC, why ASIC is required, the answer lies in the next question, why we require microcontrollers, though we have the microprocessors. So basic thing is there that cost effectiveness and the less functionality we require. So suppose you have to incorporate some job, you have to incorporate some task in a device, like you want to create some robot or you want to create some toys, electronic toys. So in that case, you may require some volume production. And if volume production is there, then surely taking microprocessor or bigger, bulkier devices for small operations, it will not be fruitful. So it is better to have the specific ICs which are going to perform this job. So now, if you talk about that, you have one toy car, and in that car you have to just have the steering application. You should have some controlling application that the car should move, that the car should stop. For that, if suppose you are going to incorporate a microprocessor, which is giving you much more functionality, but cost is more, as well as you are not going to use all the functionalities which can be provided by the microprocessor. So it's better to have microcontrollers. And if suppose you have very specific application, though microcontrollers are also not applicable in that, and cost will be higher, so we go for ASIC devices. It means application specific integrated circuit. It means for some automobile application, we have different IC. For some toy or electronic multimedia application, we may require another kind of specific IC. So point is that we have to create smaller ICs which may be applicable for different applications. And since we are going for the volume production of that IC, the overall cost of the IC also becomes very less. So this is the reason why we are moving towards the ASIC, application specific integrated circuits. So before moving to the ASIC, we are also try to find out what are the different generations of the VLSI, then what are the recent technologies which are running, and then we will switch over to the ASICs. So what are the interesting facts about the VLSI? That about 30% of the all electronic equipments consist of semiconductor components. There may be some other devices like LEDs, laser devices, some other electronic applications are there where we do not require silicon as a material, we may require some gallium arsenide based devices, gallium arsenide phosphide, or some other kind of devices we may require. So about 30% of all electronic equipment consists of semiconductor components. And about 20% of all ICs are ASICs, application specific integrated circuits. So in the year 2000, the volume world production of semiconductor component was around $300 billion. And channel length, which was at that time in 0.13 micron, it means 130 nanometer. In the year 2000, now it reaches to the 10 nanometer. It means the Intel has produced 15 or 16 nanometer devices, MOSFETs, and now it is creating the microprocessor based on 22 nanometers, as well as now they are working on 16 nanometer, and they are approaching towards the 10 nanometer technology. But because of some scaling issues, because of some different issues which are there in the MOSFET, earlier MOSFETs, now we are switching over to different kind of MOSFET design. We'll talk later about these designs also. So if we talk about the evolution, you already know about that. Transistors were earlier first developed in 1950 in Bell Laboratories, and integrated chips, or you can say this is the greatest boom in that industry that led to the fabrication, and that is incorporated in 1960s. Microprocessors were first introduced. It means that first microprocessor was Intel 4004 that was developed in 1970s and produced in the market. Then era of digital signal processors came into the existence. It means now if you talk about the mobile phone, they require microcontrollers as well as they require digital signal processors. And in 1990s, FPGA and ASICs came into the existence. And after 2001, we are working on system on chips. It means whole of the micro computer is created on a one single chip. So first electronic computer was produced in 1946, and that was ENIAC. Dawn of transistor age started after in 1947 when Bardeen and Breton create point contact transistor with 2 PN junctions, and that has produced around gain of 18 at that time. In 1951, Shockley developed junction transistor, which can be manufactured in quantity. It means in a integrated circuit form. After that, in mid 1959, Noyce developed the first true integrated circuit using planar transistors, back-to-back PN junction for isolation, and back-to-back. I hope you remember that if suppose we reverse bias the junction between the two transistors, then we can isolate them. Diode isolated silicon resistors and SiO2 insulation with evaporated metal wiring on the top. In 1970, Intel started selling a 1K bit RAM with the 1103. Its density and cost make it the only game in town at that time. In 1971, Ted Hoff at Intel designed the first microprocessor. The 4004 had 4-bit buses, a clock rate of 108 kilohertz. It had 2300 transistors, and it was built on 10 micrometer process. So if we talk about the first 30 years of the VLSI, we talk about from 1970 to 2000, then first Intel processor was 4004, and it was produced in the market in November 15, 1971, and it was using 4-bit ALU with 108 kilohertz clock cycle, around 2300 transistors, and it was using 10 micron technology. And in 2000, Intel Pentium 4 came into the existence with in August 27, 2001, with 32-bit architecture of bus and 1.4 gigahertz processor, 42 million transistors. More than that, it means afterward 55 plus million transistors were there in that Intel 4 Pentium processor. And it was using 0.18 micrometer technology. Now, if you talk about the recent technology, that is on 16 nanometer and 10 nanometer also. So earlier the chip size was 3 cross 4 mm, and then in Intel Pentium 4 it was 146 millimeter square IC. So in April 2001, a news was by Intel came into the newspaper that the world's first 3D tri-gate transistors on a production technology and new 22 nanometer transistors have unprecedented combination of power saving and performance gains. The world's first demonstration of 22 nanometer microprocessor, codenamed as Ivy Bridge, that will be the first high volume chip use 3D tri-gate transistors. It means 22 nanometer beyond, we are using tri-gate transistor. We are not using the earlier MOSFET configurations, earlier planar MOSFETs. Now we are using tri-gate transistors. So if we talk about the MOSFET evolution, how the MOSFET design is changing, the first was already, you know about that, is a bulk silicon planar type of MOSFET, in which we have the gate, we have source and drain, and channel is formed whenever we are applying some gate voltage, and when we are applying some drain voltage, then current will flow. Depending upon type of carriers in the channel, we may apply the different voltages, whether that is positive or negative, but source and drain will depend upon the voltage difference. After that, because of the leakage current flow inside the bulk from the source to drain, which is uncontrollable, the UTB planar SOI devices came into the existence. It means, first of all, there is a substrate, and over that we are developing oxide layer, then we are having the epitaxial layer of the silicon, and we are creating the source and drain region within that region of epitaxial layer. And because of that, the leakage current through substrate substantial decreased. Now point is that still when we are decreasing the channel length, what is happening basically, the DIBL effect, subthreshold slope, such kind of problems were arising, and to reduce those problems we changed to the another technology, that if suppose we have not only one gate, we have two gates from two sides of the channel, then more controllability will be there with the channel current. Fine. So if suppose we have one gate up and one gate down, in general it is basically not like that, up and down, it is like sides. One side there is gate, another side there is a gate, and we are applying the gate voltage, and because of that we are having much control over the electrostatics. Then still, if you want to have the more control over the electrostatics, we can switch to the tri-gate devices. It means not only we are having the side gates, we are also having the gate at the top. If we want to have more and more possibility of such kind of controllability on the current and reduce the leakage current, reduce the DIBL effect, have the same subthreshold volt, less leakage current. It means leakage current means nothing but the I off current. So I on current basically changes with the same proportion with the drain voltage, but I off current changes with the drain voltage. It means suppose if we have increased the drain voltage 100 times, the I on current changes to 100 times, but I off current maybe it is changed by more than 100 times, and that I off current is basically creating the change in the threshold voltage. Also basically it is changing the I off current, so more leakage current will be there. So if we want to reduce this DIBL effect and other undesired effects, we may switch to the tri-gate to pi-gate. It means the channel is basically covered more from the side. If again we want to have more controllability, we can again cover the channel from the below, but not completely. So that is ohm gate. And if we can cover the whole channel by the gate itself, then there we can think of that this kind of effect of DIBL and subthreshold slope problem may be highly decreased. So that is gate all around.
But sir, by using GA, we may have some disadvantages also.
True.
So What about those? In case of like reducing leakage current or
Parasitics will be more in that case.
Yeah.
If we are having the gate all around, then parasitics will be there. But if we compare with the previous generations and if we are finding more advantages, then surely we have to move towards the gate all around. Maybe if we can have some other technology by which we can reduce this parasitics, then obviously it will be a better choice. But if we compare with the tri-gate devices, gate all around is producing or providing much more benefits. So at present, we can say that this is the better option. But we cannot say best because maybe in future we'll have better devices. So what are the advantages of the integrated circuit? Why we are fabricating it? So first thing is cost. If we are going for the volume production of the ICs, if suppose we have to fabricate one IC and we have to go for the fabrication, you can think of how foundries are going to charge you more than 20 lakhs in rupees, basically. I'm not talking about the dollars. So more than 20 lakhs for one single chip. If academic person moves to the foundry and creates some device and asks foundry to allocate some place on the chip and provide some special consideration to that and give that chip back to the academician and ask, and then academician is going to test the real-time performance of that chip. The foundry is going to charge very high. But if that chip is going for the high volume production, then surely the cost will reduce. And that is the biggest advantage of the integrated circuit, that we are having the reduced cost. Also, we have the more reliability in comparison to the discrete circuits, where there is the problem of short circuit, open circuit, and so many other problems are there. Even we cannot procure that circuit for a long. If some short connection is there or connection is open, then again we have to check the bulkier device, and it's tough to check it. If we talk about the microprocessor is discrete, then you can think of again rechecking of that microprocessor is very, very tough. Then better solution will be to create that microprocessor again. So that thing also happens in a class also, when you are going to ask the student to create the circuit and they come to you and ask, sir, this is not working, kindly check it. So you say, okay, it's better I just make it and reassemble it. I'm not going to check it again. So next thing is reliability. So that kind of open circuit, short circuit problems are not there in the case of IC. Only you have to just mount that IC and the specific functionality can be achieved. Third point is the speed. In comparison to the discrete components, we are having much nearer devices, as well as less interconnections are there, or you can say smaller interconnections are there. So the speed is also increased. And the last one is low power, because interconnects are less length of interconnection is there, so that power dissipation will be also less. So after the advent of IC development technology, more research started to embed more transistors in a single wafer, and then in 70s microprocessors were developed, and microprocessors are nothing but a CPU on a computer. We can classify the ICs. Basically, we are not considering the microprocessor and microcontroller. We are talking about the other type of ICs. So one is ASICs, application specific integrated circuit, and these are basically created to generate some specific applications, as we are discussed about that. If we have to make one toy car or some smaller robots, then we have to go for such kind of ICs. We cannot use or incorporate the microprocessors to perform that small application, and that because cost will be higher, and we are having unutilized sections of the microprocessors and also the microcontroller. So there are so many examples like hearing aid, cell phones, TV controller, etc. They are using the ASICs. So anything is specific for one application cannot be used for other application, and that is that are ASICs. And this concept became very popular when volume sales is required. If suppose you are going to create one device and you want a specific IC to be developed for that, and that is only one single application, hopefully ASIC is not going to be a better option, because in that case the cost of fabrication of that IC will be very, very high. So it is only applicable when you are requiring the volume production. So this concept became very popular when volume sales is required. For example, cell phone production. So in cell phone, there are so many applications which are basically handled with this ASICs. Next is FPGA. So you can say FPGA is also a type of ASIC. It means ASIC is a set and it is a subset of that. But because of application nowadays, FPGAs are considered a different entity in comparison to ASIC. So field programmable gate arrays are similar to digital signal processors. They are programmable. DSPs are also programmable and can be used for different processing application, but FPGAs are programmed for specific application. In general, FPGAs are used in academia, where we are constructing the device. It means we are constructing the device in some front-end tool, and then we are transporting that net list to the FPGA, and then we are just trying to find out how this circuit or device is going to work in a real-time mode or real-time application. So FPGA became popular for small scale applications, prototyping, and university research. Develop program with the software tool, upload to FPGA, and then we can run and test the device in real time. And third categorization is basically SoC, that is system on chip. For example, input output, memory, DMA, these are embedded on one single chip and we are utilizing it. And in general, it is called as embedded system. So we have the different application, different domains of application, and depending on that domain, we are using ASIC, FPGA, or the SoCs. What is the difference between a standard IC and ASIC? So standard ICs are basically, you can compare that different generations were there, SSI, LSI, and so on, and we are creating the microcontroller or microprocessors like that. Also multiplexers, encoders, gates, which are using in the day-to-day life in the laboratories, that those AND gate IC is there and you are just using that IC and creating the application. Application specific integrated circuits are basically an IC customized to particular system or application. It will not be used for other application, and that is termed as custom ICs. So concept started in 1980s. Chip for toys, automobile control chip, different communication chips, these are the example of the ASICs. Digital designs became a matter of placing of fewer ICs or ASIC plus some glue logic also. So reduced cost and improved reliability. We are achieving this thing in ASICs. So different type of ASICs are, ASIC can be categorized into full custom ASIC and semi-custom ASIC. Already you know about this difference of full custom and semi-custom design styles. So basically full custom ASIC is that we are starting from the scratch. We are starting or customizing each and everything of the circuit, and then we are fabricating it. Another part is semi-custom ASIC, and that is divided into three different categorization. One is standard cell-based ASIC, gate array-based ASIC, and programmable ASIC. The programmable ASIC can be PLDs and FPGAs. So I told you earlier that FPGA is a type of ASIC, but nowadays FPGA is treated separately. So we are saying that ASIC is different and FPGA is different, but basically it is a programmable ASIC. So full custom ASIC is nothing but in which basically we are all logic cells and mask layers are basically customized. Everything is customized, or everything is started from the beginning. Semi-custom ASICs are that all logic cells are pre-designed, and some or possibly all the mask layer or the metal layers are basically customized. So full custom ASICs, basically if we talk about, then we can talk full custom ASIC design makes sense only when no suitable existing library exists. Point is that you can think of that if you are designing the we can just differentiate what is the front end tool and back end tool. Can you tell me what is the difference between these two?
Front end we can directly connect with user. A user can directly interfere or
No,
communicate
we
with
both, suppose we are the user. User is going to create design in both of the front end and the back end tool. What is the difference between these two?
As per I know, maybe backend only through OS backend communicate or something like that.
No, basic thing is there that in front end tool, we already take the help of the design library. In the library, some gates or some devices are already there, and we are basically utilizing them. We are not creating those gates. We are taking the gate, and then we are making the interconnections, and then we are making our device and forwarding that netlist to the FPGAs and just trying to verify the working of that. But in backend tool, we have the facility that we can start from the MOSFET design. If suppose we talk about the Verilog is giving you the facility that you can have the MOSFET level design, but you are not going to change the parameters of the MOSFET. That parameter is already described. Only you have to make the interconnection. Suppose in Verilog we have the source, drain, and we have some specific functions for the MOSFET, for PMOS and NMOS and CMOS, and we are basically having the connections. We are using some specific syntax and we are defining the connection. We are not going to define the technology of that MOSFET. We are not defining any doping concentration, parasitics, and nothing we are describing in it. We are simply taking that from the library and then we are interconnecting. So in general, what we are doing, we are basically customizing the interconnections, how that different entities are connected. We are not defining the technology. That is the point that this full custom, front end tools are termed as technology independent language. Fine. While in backend, basically we are working. We are basically starting from the MOSFET level design, and we are basically defining the whole of the construction of the MOSFET. We can define the dopant level. It means when we are attaching the model file along with that simulation. Then in model file, basically we are defining the different parameters of the technology. Different parameters of the MOSFET as per technology. And those parameters are defined by the foundry itself. It means when the foundry made that device, suppose 22 nanometer MOSFET is designed, then what are the value of the parasitic source to drain capacitance or drain to gate capacitance? What are those parasitic capacitance values? What are those parasitic resistance values? What are those values? That is defined in the model file. You can just open the model file and you can find out different parameter values are given. And then simulation is performed on the basis of that model file. Fine. So in that we are basically defining each and everything. We are defining MOSFET, we are defining the device, as well as we are defining the interconnections. So you can think of that this is the basic difference between the full custom design, where we are defining each and every part of the circuit. We are defining each and every parameter, while in semi-custom design, we are just assuming that the library is having the component and we are taking those components and interconnecting them and forming the device. So full custom ASICs design makes sense only when no suitable existing library exists. We do not have any library. We have to create library first. Existing library cells are not fast enough. If suppose if we want to change the technology. In case of front-end tool, basically that is technology independent. We don't have any access of that. We cannot change it. But in backend tool, we have the processing. We have the different technology files, and accordingly we have to define each and everything. Then we have to simulate whether our design is working in that particular technology or not. So basic thing is there. Why we require full custom design? First point is when no suitable existing library is there, or existing library cells are not fast enough. It means we have to customize those library cells also. We need to change the design also, design of the multiplexer also, because as you move forward you'll see that different ASICs are there, and those ASICs are designed. If suppose we talk about Altera or Xilinx, they are based on different basic cells. Some are based on the multiplexers, some are based on different architectures. So if you just try to find out different architecture, if suppose those multiplexers or those RAM devices, SRAM connections are not basically up to the mark or not fast enough, then you have to redefine them. Then we have to use full custom. The available pre-designed or pre-tested cells consume too much power that a design can allow. It means if the existing cells are using more power, the available logic cells are not compact enough to fit, or ASIC technology is new or so special that no cell library exists. So these are the points where we have to redesign our cells library components, and then we have to utilize them. So include some possibly all customized logic cells have all their mask layer customized. It means once we have defined or designed our library components, then we have to utilize those library components and make the interconnection between those, and we have to create our device. Offer highest performance, lowest cost. We are basically trying to compare it with the semi-custom design. Then this is going to offer highest performance and lower cost, but at the expense of increased time, design time, and higher design cost, because we are doing each and every effort. So time will be more as well as cost will be higher. Some examples are high voltage automobile control chips, analog to digital communication chips, sensors and actuators. So that we have to design in a full custom hierarchy. Another is semi-custom ASIC. Semi-custom starts with the prerequisite thing. It means you already have the library components, only you have to make effort in interconnection. What are the best interconnection you can make? Suppose if there is a big circuit, complex circuit, and you may have worked on ORCAD or some other tools. So there is a auto routing type of phenomena. So what basically auto routing is doing? Auto routing or placement.
That is the interconnection.
Interconnection already is there.
Shortest interconnection between all the.
Shortest. So how you achieve this shortest interconnection? Very simple. Place the connected device nearby, and those are not connected, place them apart. So basic thing is there, we have to work on this interconnection of the devices. How we can efficiently interconnect them and get the better out of that. So basically use logic blocks from standard cell libraries, other mega cells, full custom blocks, which are already defined in the full custom design. You can use them directly. System level macros or functional standard blocks that can be used, and then we work on the interconnection. Get all mask layers customized, that is transistors and interconnections. Then manufacturing lead time is around 8 weeks. Well, for full custom design, it is not defined earlier. You can see that depends upon the complexity of the design. More complex, more time it will take. Less efficient in size and performance, but lower design cost. Lower design time and lower design cost. So if suppose we talk about the cell-based IC, basically we have a wall of standard cells from forms of flexible blocks Then we will have the metal 1 layer, metal 2 layer, and so many layers depending upon the complexity of the device. If we talk about the microprocessors or recent microprocessors, they may require 12 metal layers for the interconnection. While for the memory devices, we may require lesser number of layers. Can you tell me why this is so? If suppose you have to make a hard disk, which is a memory device, and another is microprocessor. In microprocessor, we are requiring a much higher number of layers, while in memories, we may not require higher number of layers.
We are replicating the same thing in memory.
Yes, that is the point. In memory, basically, we are creating one type of block and then replicating it and making the interconnection. So we may require less number of metal layers to create the whole interconnection. While in the case of microprocessors, there is no repeatability. So we have to create each and every device. We have to provide interconnection for each and every device. So the requirement of the metal layers will be higher. So metal 1, metal 2, metal 3, these are the layers of the different interconnections.
Talk about hard disk, that is magnetic storage.
Yeah, true. But I'm talking about if suppose we have to make RAM, ROM of such a kind of device which are only SoC devices, then we may require lesser number of layers in the same technology.
Solid state.
Solid state memories. So metal 2 may be used in feed-through cell to cross over cell rows that use metal 1 for wiring. Other wiring cells like spacer cells, row-in cells, and power cells are also there. Depending on, even though you can say clock devices are also there, clock interconnections are also there. Clock cells are also included in that. Another semi-custom, it means earlier we are talking about the standard cell-based ASIC. Now we are talking about the gate array-based ASIC. A gate array or masked gate array or pre-diffused array uses macros to reduce turnaround time and compromises a base array made from base cell, that is primitive cell, already that is defined in the library. So there are basically three types of gate array logics. Number one, channeled gate array, channelless gate array, and structured gate array. If we talk about nowadays, basically we are very much interested in structured gate array. So I will talk more about that structured gate array later on, because this structured gate array is providing some way working in the mid between ASIC and the FPGAs. So first one is channeled gate array. So in that channeled gate array, only the interconnections are customized. It means between the row of the different CLBs, different logical blocks, we are working on the channels. We are working on the interconnection, and we are defining there is some channel, and we have to interconnect them using that channel area only. So the interconnect uses predefined spaces between the rows and the base cell. It means when we are basically going for the placement and placement is along with that floor plan. Floor planning and placement is there. So basically first process is that we are allocating the spaces to the blocks depending upon whether they are interconnected or not. If they are interconnected, they will be placed nearer, and if they are not, then they will be placed farther apart. Also, we are taking consideration of the power dissipation of the devices. If any device is having higher power dissipation, another device is also having the higher power dissipation, so we have to place them such that overall distribution of heat dissipation should be also uniform. It should not be that one part of the chip is having higher power dissipation and another part is having very lower power dissipation. That part will be considered as black part then. So when we are placing the devices, we are also providing some space for the routing. That is termed as channel. So channel can be a box type of channel, or it will be 2D channels, 2D and 3D channels. Manufacturing lead time is between 2 days and 2 weeks in this case. Almost same time will be there if you find all the different gate arrays. Same time you will find. Another one is channel-less gate array. So point is that we are not defining any channel in this case. Only we are placing the devices, and wherever we are getting the routing part, we are getting some space. We are just channelizing our interconnections, and we are making the interconnections. So it is also termed as channel-free gate array, sea of gates array, or SOG. Only the top few mask layers are customized, and manufacturing lead time again in this also the 2 weeks.
So, if we compare with channeled or channelless, in which ASIC that interconnection length will be more? Path length.
Basically, it depends upon the placement of the devices.
No, if we
It
compare
is highly
both
dependent.
Same circuits, design will be same, blocks arrangement would be same. But if we compare in both of them gate array, in which
You will find not so much difference in that. Basically, first of all, we go for the placement, floor planning and placement. We have placed the devices, then we are making the going for the routing purpose, and after that we go for the compaction purpose. If suppose we have done the placement and then we have done the routing, and in routing we are facing a problem. We are not able to connect the devices. Then again we have to move back to the placement. So after the placement, then there is a routing, and then there is a compaction. In general, compaction means whatever channel region is left which is unrouted, which is not utilized by the routing. So we are compressing the whole chip from all the directions. So ultimately you will find not so much difference between these two, but in channel we will have the possibility that we are having the well-defined region. We will have the easier process, you can say, that we have to pass through this only. And in channel-less, we are not defined with that we have to always route our interconnection through this path only. If we are finding another way, we are just routing it. So efforts may be more in the case of this one, but nowadays we are not doing this thing manually. It is already, it is you can say machine automatic process. We are having so many tools, and those tools are working. In CAD tools, basically we have this facility of automatic routing. You can think of, if you are going to make a big microprocessor, manually you can do nothing. So CAD tools are always necessary, and this is also the one thing that as the technology is increasing or enhancing, the CAD tools are also not capable to keep the pace. This is also disadvantage towards this VLSI design, that if we have the CAD tools also with the same pace, then surely we'll have the better chance of changing the technology. So next one is an embedded gate array, or you can say structured gate array. Only the interconnect is customized. Custom blocks are also that can be added into this, and the same for each design, and can be embedded. Manufacturing lead time is between 2 days to 2 weeks, and almost the same manufacturing time is there, only different mechanism we are providing. And last one is programmable ASICs. Programmable ASIC, or you can say the CPLD or FPGA type of chips are there. What is the full form of CPLD? Complex Programmable Logic Device. And FPGA, Field Programmable Gate Array. So in this kind of device, basically what we have the different gate arrays, we have the input outputs, and we have the possibility of interconnection. It means that can be anti-fuse technology, or that can be based on SRAM, or that can be based on multiplexers. Depending upon that, what we have to do, we have to write a program, and in that program we are defining how the different gates are interconnected and how they are going to perform the device, create the device. So in this case, you can just see that interconnection wires are basically red in color. So they are basically devices are centering around these interconnections. So we can fuse or anti-fuse technology use the fusing of the interconnection, and then the interconnection will be formed. It is just like you can think of that different relays are there. So if suppose we have the relays in between the devices, so if the current is passing, then relay will be on and that device will be connected, and if relay will be off, that device is not connected. So depending upon the program, those different logic cells will be interconnected, and then we can have the particular design fabricated on the FPGA. Not fabricated.
Connection and both logic array, both are programmable.
Yes. Programmable means what? Basically, we are creating the design. It means in front end tool, suppose that is we are writing a program. So in program, basically we are defining that these are the cells and how they are connected. And then we are going to create the netlist, and that netlist will be transported to the FPGAs. And according to the netlist, different logic gates will be connected, and input output will be provided. So input output ports will be there, blocks will be there, and they are connected. So if suppose FPGA is there, you have seen that board. So when you provide some press some button, suppose you have created one device, so you have to just check the different possible combination of input, and you have to just verify that these are the different possible output has to show. So that thing is there. So if suppose we compare FPGA based ASIC design, so there are three different logics: FPGA, discrete logic, and custom logic. So if you just compare on the basis of following parameters, you can see that FPGAs are providing you much effective type of configuration in comparison to the discrete and custom logic designs. Any question? Different categorization of FPGAs. These are based on different, whether they are based on the functional blocks we are using, based on programming technology we are using, or that is based on gate density we can have, as well as the chip architecture. It means what type of routing style we have to adopt. So based on functional unit logic cell structure, we can have the different categorization like transistor pairs, basic logic gates, NAND NOR, or based on multiplexers, or based on lookup tables, wide fan-in or and OR gates, fan-in, fan-out. If it is based on programming technology, then it will be anti-fuse technology, SRAM technology, and EEPROM technology. And gate density, it means what gate density we are having, what gate type of gate array we are having. According to that, we can categorize FPGAs. So one by one, basically, we are going to talk about the different programming technology. So FPGA architectures, basically different organization or companies are there like Xilinx, Actel, and so on. So they are basically having the different functional blocks, and based on those functional blocks, they are creating the design. So if you talk about the Xilinx, basically it is based on the RAM blocks, and implementation will be there in the terms of truth tables. While in the case of Actel, it is based on the multiplexer technology. It means different multiplexers will be used to create the different gates, and then those gates will be applied to have the different designs. So it will have some build Boolean functions using multiplexers. And third one is logic gates, flip-flops, such as carry chains used for high performance computation. So if we talk about this Xilinx XC4000 CLB structure that you have seen already, that Xilinx is based on RAM blocks. So different RAM blocks will be there, and those RAM blocks will be used to create the different gates, multiplexers, and those multiplexers will be applied to create the designs. And basically it is based on the truth table. Second is Actel logic module structure. It uses anti-fuse programming technique based on channeled gate array architecture, and logic cell in this case is multiplexers, which can be configured as multi-input logic gates. So we already know how to create different gates with the help of multiplexers. multiplexers. So those multiplexers are going to act as a basic building block, and with the help of those multiplexers we are creating different gates, and then those gates will be used to create different digital designs. Altera is basically using flex or max logic element structure. So it is SRAM based lookup table based architecture, and again SRAM will be used as a logic element, and then we are going to create the different designs. So if we summarize different type of logic cells, FPGAs from various vendors, so it depends on basically architecture, gate density, basic cell structure, and programming technology. So this table is there, I think so. I should not dictate whole of the table, because Actel, QuickLogic, Xilinx, Altera, Concurrent, Plessey, these are the different vendors which are providing you the FPGAs, FPGA modules, and they are selling those FPGA modules to different organizations, and depending upon their capacity, basic cell, and programming technology, and depending upon your requirement, you can choose anyone. So programming technique, basically there can be three types of programming technique. One is anti-fuse technology, second is static RAM technology, and third one is EEPROM or E2PROM technology. So anti-fuse technology is basically invented at Stanford and developed by Actel, opposite to the regular fuse technology. So normally an open circuit, until a programming current is there, it means if suppose there is a programming current, then only the connection will be made, otherwise it is going to act as a open circuit. In general, if we talk about a fuse circuit, it means it is the reverse thing. So normally open circuit is there until a programming current about 5 milliampere is forced to pass through it. So two types are there. Actel PLICE, it means programmable low impedance circuit element, and that is a high resistance poly diffusion anti-fuse is there. And second one is QuickLogic's low resistance metal to metal anti-fuse technology. So in this, basically direct metal to metal interconnections are there, and higher programming current reduce anti-fuse resistances, and then connection will be made. Disadvantage is that unwanted long delay will be there in this case. Second is static RAM technology. So it is basically so SRAM cells are basically based on lookup tables to implement the logic, or you can say in truth tables, in a form of truth table, and embedded RAM blocks will be used for buffer storage, and as control to routing and configuration switches that can be developed. Advantages are allows in-system programming and suitable for reconfigurable hardware. It means same FPGA kit can be utilized again for the different program. Once you just remove that program, erase that program, again all the elements will be in an open form and no interconnection is there. But when you again reprogram it, again the different circuit can be configured. You can just visualize it. So there is a chip.
1T SRAM.
I think I guess it is made up of 6 transistors.
There are different configurations. Are there?
2 NAND NOT gates.
2 NAND gate,
For storing.
not gates. It is basically forming a feedback through.
Yeah. Storing it.
So basically it is depending upon read and write operation. If it is a read operation, then it is different, working different. It means only in the output you can read the things, and whenever it is write operation, then you can change the stored element. It means whatever is stored in that loop of that NOT gates. EEPROM and E2PROM technology. Cell is almost as small as anti-fuse. Floating gate avalanche MOSFET technology is used. In short, it is termed as FAMOS. under normal voltage, transistor is on. With programming voltage applied, we can turn it off to implement other logic. Is that okay? I'm moving fast. Exposure to UV lamp, and we can erase the programming. Fine. It means if suppose it is EEPROM, but if it is a E square PROM, then it is electrically erasable. Use E square PROM for quick reconfiguration, and also ISP is possible. So different types of configurations you can see. It is nothing but basically the type of MOSFET configuration, and depending upon the logic, whether that channel is formed or not, current will be there.
There are separate technologies for EEPROM and EEPROM.
True, obviously it should be.
Floating gate amount MOS technique is used for EEPROM.
Mm.
I'm not remember if it's for EEPROM, which is another type. Some other type of MOSFET is used.
Other type of MOSFET for electrically erasable. Okay, just think of that. If suppose we have the EEPROM technology and we have to erase the content of the device with the help of light. So the surface of the chip has to accept that light. If suppose it is silicon only, can it accept that light, UV light, and erase the things and or perform the operation? Basic thing is there that refractive index of the device has or the material has to change when the light is falling, and accordingly the operation has to be done. So the configuration of those two type of devices will be widely different. E square PROM, you can easily understand that if there is a current, then whole of the thing will be vanished. It is electrically erasable. But UV, it is accepting the light and then it is performing some operation. So there should be some provision for that acceptance of the light. Normal silicon is not utilized in general for the light application.
What I'm saying is that floating gate, this technique is used for EEPROM, not for EEPROM. I guess or something like that. For a floating gate, advanced MOS is used for only one technique.
Mm-hmm.
Some other technology is used for
E square PROM, obviously the simple MOSFET can act. In E square PROM, simple MOSFET, which is silicon transistor based MOSFET, will act. But for UV PROM, that will not act. So what will act?
That's what I don't remember it, but the thing is that a simple MOSFET will act for RAM, not for ROM.
RAM for not for ROM.
Yeah,
Okay.
For RAM, not for ROM. But that connection has to be permanent
Mm-hmm.
in case of ROM. And that is what you have a gate that is floating type, and when you expose it to the light, that
I'm not talking about the light. UV is separate. Huh?
Yeah.
We are talking about electrically erasable. You're saying that normal MOSFET is not going to work.
For normal MOSFET is used for RAM, not for ROM.
True hai. That is true, because we want the permanent storage in ROM. So if smaller current will be there, then it will be changing the device pattern.
Yeah, so that is your high voltage.
So normal MOSFET configuration is not there, but it is like a MOSFET. I have not said that it is MOSFET. I said it is MOSFET like pattern in which gate is there, source drain is there, and we are just having the channel formation. If that channel formation is there, then there is the storage or not. Right? So this is big summary sheet. If suppose you want to study, that is big one. So programmable ASIC technologies, which are given by Actel, Xilinx, Altera, and the Xilinx EPLDs. So you can think of different programming technologies are there. In Actel, there is a polydiffusion antifuse technology. In Xilinx LCA, there is erasable SRAM ISP. Altera EPLD is giving you UV erasable EEPROM and E square PROM also. while Xilinx CPLDs are giving you the UV erasable PROM. And size of programming element, process, programming method, programming technology. These are the different parameters. Based on that, you can choose the different FPGA provided by the different vendors, and according to your requirement, you can work on that. So if we talk about the ASIC design process, first of all, there is some design entry. It means there is some schematic entry or HDL description of the device. It means suppose if you have to create the device for some specific application, so you have to just write that program in some SDL tool. That may be VSDL programming, that may be Verilog programming. So first of all, there should be the design entry in the form of the program. Then there will be the logic synthesis of that HDL program using Verilog, suppose, or VSDL. You have to produce the netlist, logic cells, and their interconnect details. Then there is system partitioning. It means divide a large system into ASIC sized pieces. Then there will be pre-layout simulation. If suppose device is having some layout, you have to check whether that layout is properly working or not. If suppose that pre-layout simulation fails, then we have to again go back to the system partitioning and you have to do the process again. But if it passes, then you have to go for the floor planning, and then you have to go for the placement of the different modules, and then routing, and then extraction, and then there will be the post layout simulation. And every step, basically there is a checkpoint. If after every step, if that fails, you have to go back. Then this is the Altera FPGA design flow. Basically you can see that first of all there is a design entry, then there is a pre-layout simulation, and that ADIF or VSDL netlist entry will be given to the place and route tool, and then you are going to frame or make the circuit. Also you can go through the synthesis, and with the synthesis, after synthesis you are generating the netlist, and that is given to the place and route tool, and you are generating the ASIC. Xilinx FPGA design flow, basically it allows third-party design entry. Software accepts their generated netlist. Basic advantage with the VSDL is that it is platform independent. That suppose if you have generated one program in one computer using some tool, using some Xilinx tool, and if you are having another VSDL tool, you can run that program. So it is basically third party can design that software, design that device, and that design will be accepted by the Xilinx, and then generated netlist can be utilized. So you can see that use pin to XNF and wire to XNF software to convert the netlist file into XNF. .xnf extension will be there, and then mapping and merging program will convert that XNF file to create unified netlist based on NAND and NOR gates, and then .map file will be generated. Then map to LCA program does fitters job. It means fits the things and produces unrouted .lca file. And after that, the APR or PPR software does the routing job. Post layout netlist will be generated, and then you are going to test the things after, or it is termed as the post layout simulation of the device. So now we talk about another or kind of ASIC, that is structured ASIC. So a structured ASIC falls between an FPGA and standard cell-based ASIC. It is not, we are saying that it is ASIC or FPGA, somewhere in between. So structured ASICs are mainly used for mid-volume level designs. The design task for a structured ASIC is to map the circuit into a fixed arrangement of the known cells. Properties of this structured configuration is that the cost will be reduced, implementation engineering effort, the cost will be reduced using that in engineering effort as well as mask tooling charges. Performance will be higher in this case. Low power consumption will be there, less complex, as well as small marketing time will be there. So architecture will be having two main levels. One is a structured element and another is array of structured elements. So combination and sequential functional blocks will be there, and that can be logical or storage element. So these are already known to you. Prerequisite kind of thing or library structures will be there. And then array of structure element means uniform or non-uniform array styles will be there, and fixed arrangement of the structure element are there. So overall architecture is based on the fabricated input output cores, embedded RAMs, and C of gates. So main implementation steps are RTL design. First of all, we go for the RTL design, register transfer level design. Then we go for the logical synthesis. It means maps RTL into the structured element. Then we go for the test insertion. It means we improve testability and fault coverage will be there. And at last we go for the placement. So maps each structure element onto the array elements and places each element into the fixed arrangement depending upon the requirement. Fifth one is physical synthesis. It means then we go for the physical synthesis, which improves the timing of the layout, optimizes the placement of the each element. And then we go for the clock synthesis, distribute the clock network, minimizes the clock skew and the clock delay. Basic thing is there that when we are creating the chip, clock distribution and the power distribution, these are the two very, very important steps. Because if you talk about the clock distribution, if suppose there are some synchronous as well as asynchronous blocks we have to connect. So suppose if there are two blocks which are synchronous, but they are placed in two different locations in the chip. So our task is that the clock signal should reach to both of the designs, to both of the devices in same time. But it may be that the clock generator is here and one block is much farther apart and another block is very nearer to the clock generator. Then point come how we interconnect those two devices so that the clock will reach to those devices within the same time. So somewhere clock generator is there. We also create some clock distribution points in the chip. So many distribution points will be there, and we have to connect to the different distribution points such that the synchronous event will start on the same time. Similarly, the power distribution, because as the interconnect length is increasing, obviously through the interconnect power, or you can say heat dissipation is there. We have to require some amplifiers, something like in the mid, so that same logic level should reach to the different blocks. So some blocks which are farther away, when the signal of 1 or VDD reaches to that point, it may not be VDD, it may be less than that. So we have to adopt some techniques so that same power will be distributed to the different elements. So then clock synthesis will be there. It means we have to check all the synchronous and the asynchronous devices are properly connected and they are functioning properly. And at the last there is routing. So inserts the wiring between the different elements. So clock interconnects, power interconnects, and the signal interconnects. These are the different interconnections will be there, and we have to be very careful during the implementation. Implementation issues are the logic synthesis, placement and routing all depend on the target structure element and architecture, and hence add more complexity to the design process. The completeness of the target structured ASIC library also affects what specifically can be implemented from the design. So if we compare FPGA with the standard cell ASIC, so FPGAs are easy to design, short development time, and low cost. While ASICs are difficult to design, long development time, and higher cost. But in other points, ASICs are much better than FPGAs, like in design size, design complexity, performance, high power consumption, and high per unit cost. So structured ASICs combine the best of the both, and that is why we are just tending towards the structured ASIC nowadays. So structured elements contain unconnected discrete components and could include transistors, resistors, and others. Structure elements contain generic logic and could include gate, multiplexers, lookup tables, or the flip-flops. Structured ASIC use many structured elements that contain only gates, multiplexers, LUTs. It does not contain storage elements like flip-flop. And basically these are the different fine-grained, medium-grained, and hierarchical. So in fine-grained, we are basically using transistor, resistors, and other. In medium-grained, we could use multiplexer, LUT, and flip-flop, but in hierarchical, we are not using the flip-flops. We are using only the multiplexers and LUTs. The milli-element is then combined with resistors or flip-flops. So architecture comparison, if you perform between the fine-grained, hierarchical, and medium-grained. So fine-grained requires many connections in and out of the structure elements. Higher granularities reduce connection to the structured element but decreases the functionality it can support, as well as clearly each individual design will benefit differently in varying granularities. Advantage of structured ASIC is now it is largely fabricated. So components are almost connected in a variety of predefined configurations. Having already a few blocks already fabricated, and some of the block we have to introduce again. Only a few metal layers are needed to be fabricated, and drastically it is reducing the design time or turnaround time. Easier and faster to design than standard cell ASIC. So multiple global and local clocks are prefabricated in this case, while in FPGA everything we have to fabricate. Multiple no skew, clock skew problem that need to be addressed. Signal integrity and timing issues are inherently addressed already. So capacity, performance, and power consumption closer to that of standard cell ASIC. Faster design time, reduced cost. Therefore, the per unit cost of the reasonable for several hundreds to 100,000 unit production runs. Structured ASIC disadvantage are lack of adequate design tools. That I told you earlier that the CAD tool design or the CAD software which are available, that should also have the same pace with the technology. If we are shifting from 32 nanometer to 22 nanometer, then also we should have the CAD tool that should support this thing. It means it should provide the same functionality. It means it should be able to simulate the circuit with the same 22 nanometer technology. But what happens? Technology is changed, but now we are waiting for the CAD tool to incorporate that thing also. So lack of adequate design tools, expensive, altered from traditional ASIC tools, and these new architecture have not yet been subject to formal evaluation and comparative analysis. So many companies are using existing standard cell-based CAD tools. They add product specification, specific placement tools. To maximize benefits, we need CAD tools designed specifically for structured ASICs, need updated algorithm to exploit the modularity of the structured ASICs, and clock-aware design. So need architectural evaluation and the analysis tools. So basic thing is there that what is software? Software is basically going to design the things based on the algorithms. So if technology is changed and basic algorithm is not changed, then software is not going to be able to provide that functionality. So algorithmic design, or you can say the physical design structure or algorithm, if they are not finding the same pace, obviously we will be not in a good position to fabricate the things, to provide the better environment to the user, or you can say the manufacturer. So enhancement should be made to existing EDA tools to achieve a better performance result on the ASIC architectures. The ASIC is a revolution to the business. The structured ASIC was developed to bridge the gap between the FPGA and the standard cell based ASIC. So it's all about, if you have any query, you can ask.